All right, so then I kind of want to switch gears and I want to talk about 8.2 for a little while because I didn't get the videos up for that. Yeah, I think I forgot to change the title on the first slide. So this is Inference after ANOVA. And I'll try and put up a short YouTube video that is separate from this recording of the synchronous class. This is the 8.2 stuff. So just back to my example that I was using in those videos with ANOVA, there's this thing called the WONG Baker pain scale. This is from Wikipedia. This was the only Creative Commons licensed version of the image I could find, which it's not in English, but luckily you don't have to read the words to understand it. It's just if you go to the doctor and you're in pain, they'll ask you to like sometimes point at which of the faces describes how much pain you're in, and then you can use it even with kids. So these researchers wanted to know if listening to music or to an audiobook was going to reduce kids' pain. So those were our three groups that we were interested in. And I showed you a couple different visualizations in the previous video. So I showed you the box plots where I think you can sort of see like the control group looks different from the music group and the audiobook group. The music and audiobook groups, they look pretty much the same. And then I also showed you the same data, not as a box plot, but as a dot plot. So you can see that there's like some people with really low pain in the audiobook, but some people with pretty high pain. Looks like the control, there's more people that have high pain that they're reporting. So they split the people, they were children who'd had surgery, into whether they were going to listen to an audiobook of their choice, music of their choice, or they were just going to sit quietly. And then they asked them to report their pain on that WONG Baker scale. So we did the ANOVA table from before where we had this p-value, which was 0.014. We were able to reject the null hypothesis. We have evidence to suggest at least one of the means is different. But then the thing that is sort of annoying about ANOVA is that's the only conclusion that you can come to. It's just at least one of the means is different. You can't say which one of them is different. You can just say that there is at least one that is different. Oh, I forgot that I had this in there. So if you're using software, you can get these tables from ANOVA. This is the one from R, which is what I usually work in. This is the one from Minitab. So they're going to come up with the same things, although you can see that they're a little bit different. The one for R doesn't have a row for the total. But the Minitab one does. But like the F value is going to be the same and the P value is going to be the same, no matter what software you use. And then we can also like compute the table by hand, which is something that I'm going to ask you to do on the homework and also on an exam. So we had this small p value. We could conclude that the means are different, but we don't know which ones. So that's the challenge. And so 8.2, that section is about doing inference after ANOVA. So if you wanted to know which ones were different, then you would do additional inference. And there are some different tasks that we could do, inferential tasks. We could make a confidence interval for a single mean. I think this is kind of boring. So the two that are more interesting are a confidence interval for a difference of means or a hypothesis test for a difference in means. And then if we're going to do those things, they're going to work like normal, basically like the way that we did them on the cheat sheet. So when we were doing inference for a difference in means here, we did things like, we found a t value for our hypothesis test, or we did a confidence interval like that, and we had these ways to compute the standard error. So we're going to do basically the same thing, except for instead of using S to estimate sigma, we're going to use the square root of the mean squared error from the ANOVA table. And then instead of how we've computed the degrees of freedom in the past, we're going to use the error degrees of freedom to find the critical value for a confidence interval or to compute a p-value for the hypothesis test. Like I said, I think that the confidence interval for a single mean is pretty boring. So the ones that I'm going to focus on are the confidence interval and the hypothesis test. And here's how it's going to look. So it's going to be our point estimate plus or minus our critical value times a standard error, where this is how we compute the standard error. Oh, and I apparently missed a piece of it. This needs MSE under the square root when I was making my slides. I'll go back and fix that. So for a hypothesis test, that's always our point estimate minus our null over our standard error. And again, we're going to compute the standard error as the square root of the mean squared error, 1 over ni plus 1 over nj, square root of that whole thing. So that's how we're going to do inference after ANOVA. I would like to do a confidence interval for a difference in means and a hypothesis test for a difference in means for the pain relief data. If we have time, we might go and do the one for the cuckoo birds as well. But let's start with the pain relief data. We've got our ANOVA table, and then we've got our data. And the things that are going to be really important are the mean square error, which is the mean square for the residuals, and the degrees of freedom for the error. And then we're going to need whatever means we're going to find a difference about. So I said, let's find a 90% confidence interval for the difference in pain ratings between the music condition, which had a mean of 4.8, and the control, which had a mean of 7. So those are the main numbers that we're going to need. So I'm going to do x bar I minus x bar j plus or minus t star times the square root of the MSE 1 over n sub I plus 1 over n sub j. So let's see, if we plug in, we're going to do the music and control. So then we're going to have 4.8 minus 7, which I think is minus 2.2. Plus or minus t star times, and then we're going to have the square root of 2.948 times 1 over 10 plus 1 over 10. And then we have to do some arithmetic. So 1 over 10 plus 1 over 10 is 0.2. 2.948 times 0.2. SE is going to be the square root of 0.5896, which is 0.768. I'll round to. And I erase this, I think. So now I've got minus 2.2 plus or minus t star times 0.768. And then the last thing that I need is my critical t star. The t distribution has 1 degree of freedom, and the one that we're going to use here is the degrees of freedom for the residuals, which is 27. Someone was asking how we decide which distribution to use on StatKey to find the p-value. In 8.1, where we're doing ANOVA, we're using an F distribution. And now that we're in 8.2 and we're doing inference after ANOVA, we're back to the T distribution. So I'm going to go to StatKey. I'm going to pick my theoretical distributions, and I'm going to pick my T distribution. And then my degrees of freedom are going to be 27. And then, because I'm doing a confidence interval, I'm going to do a two-tail. And then it's defaulting to 95% confidence. It's got 95 in the middle. That would be the critical value. I said I wanted to do a 90%. So I'm going to put 0.90 in here. And then that's my critical value, 1.703. So that's my critical t-value. 2.2 plus or minus 1.703 times 0.768. 1.308, and then 2.2 minus 1.308, we've got negative 3.508 to negative 0.892. And then I could interpret this. I am 90% confident that people in the music group reported pain that was between 3.5 and 0.9 units lower than for the control on average. So we're pretty sure that the music group has lower pain than the control group. It might just be like a point lower, or it might be 3.5 points lower, but that confidence interval does not contain 0. So we're pretty sure that there's a reduction in pain. So let's also do a hypothesis test. Again, we're still going to need the mean square error, the degrees of freedom for the residuals, and we're going to need some means. This time I said, let's look at the difference between the audiobook and the music condition. So in this case, our null hypothesis is that mu audiobook is equal to mu music, and our alternative is that mu audiobook is not equal to mu music. And we're going to find t equal to x bar audiobook minus x bar music over the standard error, which is MSE 1 over n sub I plus 1 over n sub j, square root of that whole thing. So in this case, I've got the audiobook 5 minus 4.8 over that standard error. So I've got 0.2 over the standard error. And the standard error is the thing that's complicated, but it's actually the same as what we found for the previous one. So we already computed this standard error, and we found it to be 0.768. 0.768. So I can actually just use that. 0.768 is going to be 0.26. So that's my t value. And my suggestion is always to make a guess based on the normal distribution. What would my guess be here? Is it going to be significant or not significant? So I think for a normal distribution, to have 90% in the middle, it goes out to 1.645, 1.645. So if it was in the tails outside of that, then it would be significant. In this case, we found 0.26. So my guess is not at all significant. So that's my expectation. Again, like the t distribution is not exactly the normal distribution, but it's good to have an idea in our head. So we're still going to use the 27 degrees of freedom, and we could go back to StatKey to figure out that p-value. Let's do it. I'm going to go back to StatKey. I'm going to click on the t distribution. I'm going to put in 27 degrees of freedom. And then I am doing a two-tail test because I have the not equals in my alternative hypothesis. And then I'm going to substitute in at the bottom, instead of that 2.052, I'm going to put in my test statistic, which was 0.26. 0.26. Whoa, that is extremely, extremely not significant. It's going to be this huge, huge p-value. Like that. So the p-value is 2 times 0.398, 0.796. That is huge. So we are going to fail to reject. So